Hello dear students, today we are going to discuss laws of chemical combination. So basically we are dealing with chemical reactions. In chemical reactions we have some laws to be followed. So what are those laws which governs a chemical reaction? So these are known as laws of chemical combination. So we are going to learn what are the laws of chemical combination, what is significance and its applications. So coming to the laws of chemical combination, we have laws of chemical combination. First, let me give you what are the laws. Under this, we have law of conservation of mass. So the first law is law of conservation of mass. The second law is law of constant composition by mass. Third law is law of multiple proportion by mass. This is by mass. Fourth law we have Gay-Lussac's law of combining volumes, or simply we say Gay-Lussac's law. Number 5 we have Avogadro's law. So these are the 5 laws which is known as laws of chemical combination. So we are going to discuss in detail what are these laws of chemical combination basically means. So first of all, let's take up this conservation of mass. Now these laws of conservation of mass, this is something what we call as indestructibility of mass. So this is what we call as universal law, which says in any given chemical reaction, mass can neither be created, mass can neither be destroyed. That means in any given chemical reaction, mass before the reaction and mass after the reaction has to be exactly identical. That means if we start a chemical reaction with 10 gram, then after the reaction, the total mass of the product formed after the reaction has to be 10 gram. If you are starting with 10 gram before reaction, after reaction, this cannot be 10.05 gram or this cannot be 9.05 gram. So if starting with the same gram, 10 gram, the mass after the reaction has to be 10 gram. This is what we call as law of conservation of mass. That means the total mass of reactant before the reaction should be equals to the total mass of the product from after the chemical reaction. So we have these laws of conservation of mass. Now these conservation of mass, this was given by a scientist known as Lavoisier. So this was the scientist who gave this conservation of mass. This law of conservation of mass, I just mentioned it, this is also known as indestructibility of mass. Indestructibility of mass. Now this conservation of mass in any given chemical reaction, that means mass before the reaction is exactly identical to mass after the reaction. That means mass can neither be created nor destroyed in any given chemical reaction. This indestructibility of mass. Now the question is why there has to be conservation of mass in any given chemical reaction. Now this conservation of mass or indestructibility of mass during the course of chemical reaction, this is based on a principle which is known as principle of atomic conservation. P stands for principal, O for of, A for atomic, C for conservation. That means in any given chemical reaction, there must be conservation of atoms. That means the total number of atoms in the reactant before the reaction should be exactly equals to the total number of atoms present in the product form. So this conservation of atoms in any given chemical reaction is the basis for conservation of mass. If the atoms before the reaction and the atoms after the reaction are same, so obviously the mass before the reaction and the mass after the reaction has to be exactly identical. So this is what we call as conservation of mass. So according to this conservation of mass, that means mass before reaction should be exactly identical to mass after reaction. So mass of the substance before reaction and the mass after reaction should be exactly identical. That is conservation of mass. And why there is a conservation of mass? Because in any given chemical reaction, there is conservation of atoms before the reaction and after the reaction. That means every chemical reaction should be a balanced chemical reaction. So in a balanced chemical reaction, the atoms present in the left hand side and atoms present in the right hand side should be exactly identical. So since the atoms remaining conserved in any given chemical reaction, the mass of the system should also be conserved. That is conservation of mass. That means suppose, take this example. Suppose we have a reaction A plus B gives you C plus D. Let's assume this is a balanced chemical reaction. So in the balanced chemical reaction, A combines with D to give you C and D. Now this C and D, this is product, while this A is the reactant. Now let's suppose, for starting with this reaction, mass of A taken for this reaction is A gram. Means A gram of A is made to react with B gram of B reactant. And after the reaction, some P grams of C and Q grams of D is formed. So mass of reactant before reaction is A grams of A and B grams of B, and mass of the product after reaction is P gram and Q gram. Then according to this law of conservation of mass, so according to this law, mass before the reaction, so mass before the reaction is A plus B gram. Now when A gram combines with B gram, that is the total mass of reactant before the reaction. After reaction, there is a formation of C and D. Quantity of C form is P gram, quantity of D form is Q gram. So therefore, mass after reaction, that is P plus Q gram. So mass before reaction is A plus B, mass after reaction is P plus Q. So according to this law, that is conservation of mass, A plus B, that is mass before reaction, should be exactly equals to P plus Q. So this is what means by conservation of mass. So the statement of this mass law is, in any given chemical reaction, mass before the reaction should be exactly same as that of mass after the reaction. That means in any given chemical reaction, mass cannot be destroyed or mass cannot be created. And why mass cannot be destroyed or mass cannot be created in any given chemical reaction? That is because in any given chemical reaction, there is always conservation of atoms before the reaction and after the reaction. So this is what we call as conservation of mass. But one point that you have to keep in mind is this conservation of mass may not be applicable to nuclear reaction. So point to be noted is in nuclear reaction, some of the mass is converted into energy. So while measuring the mass before reaction and after reaction, there may be difference of mass, but that doesn't mean that there is mass is destroyed, but mass is converted to some energy equivalent according to E is equals to mc square. So just comparing the value, you cannot say okay, but in this sort of chemical reactions, the mass of before reaction, mass after reaction does not remain same. Even in those cases, some of the mass is converted into energy, but if you converted energy into mass again, then you can apply this law of conservation of mass. So simply saying, in normal chemical reaction, mass before the reaction and mass after the reaction has to be same. So let me give you some chemical examples. Suppose we have looked at this. Carbon combines with oxygen and this gives you carbon dioxide. So if you look at this chemical reaction is completely balanced. We have one atom of carbon, one atom of carbon. We have two atoms of oxygen, we have two atoms of oxygen. Now look at this. Mass of one atom of carbon is 12 U. Mass of two atoms of oxygen is 32 U. After the reaction, we have carbon 12 to oxygen 32 U. So mass before the reaction is 44 U and mass after the reaction is still 44 U. In terms of gram, we can say 12 gram, 32 gram, and this gives you 42 gram. So why there is a conservation of mass? Because there is a conservation of atoms. Take another reaction. Like this, we have carbon monoxide combines with oxygen, and this gives you carbon dioxide gas. We have this balanced reaction. We have two atoms of oxygen on left hand side, two atoms of oxygen on right hand side, one carbon atom on either side. Molecular mass of carbon is monoxide is carbon 12, oxygen 16, 28 U. We have mass of one atom of oxygen is 16 U. We have carbon dioxide, carbon is 12, oxygen 32. So this is 44 U. Mass before reaction, that is still again 44 U. So again look at this, mass before the reaction and mass after the reaction remains same. Take another example. We have looked at this hydrogen gas combines with oxygen gas, which gives you H2O liquid. Look at this reaction. We have two atoms of hydrogen on each side, one atom of oxygen on each side. So there is balancing of atoms. Now mass of one atom of hydrogen is 1 U. So for two atoms this is 2 U. Mass of one oxygen is 16 U. Mass of water is 2 plus 16, 18 U. So look at this, mass before the reaction is 18 U and mass after the reaction is again 18 U. So Whenever we have the balanced chemical reaction, there is always conservation of atoms. Whenever there is a conservation of atoms, mass before the reaction and mass after the reaction has to be conserved. So this is what we call as conservation of mass. Take one more example, look at this. We have methane gas on combustion with oxygen gas. This gives you carbon dioxide and H2O. So first of all, we have to balance this chemical reaction. One carbon, one carbon, four hydrogen. So multiply these two by 2. We have four hydrogen. Oxygen 2, 2. So multiply this by. So we have four oxygen, four oxygen, four hydrogen, four hydrogen, one carbon, one carbon. So mass of methane. This is 16 U. Mass of 4 oxygen, that is 64 U. So mass before the reaction is 80 U. Let's look at the mass of products. Mass of carbon dioxide is 44 U. Mass of water is 18 into 2, 36 U. So mass after the reaction is still again. So whenever we have a balanced chemical reaction, mass before the reaction and mass after the reaction will always be conserved. That is what we call as conservation of mass. So for every chemical reaction, there has to be conservation of atoms. Whenever there is a conservation of atoms, mass before the reaction and mass after the reaction should also be conserved. That is same. So based on this, let me discuss some problem. We have a question. In the decomposition of impure potassium chlorate, in the decomposition of impure potassium chromate, 4.9 gram of potassium chlorate gives 1.49 gram KCl and 0.03 mole of oxygen gas. What is the percentage purity of the sample? What is the percentage purity of the sample? So we have a reaction, that is decomposition of KCl3. Amount taken is 4.9 gram. This decomposed to give you KCl and oxygen. So mass of KCl form is 1.49 gram. Mass of oxygen form is, mole is 0.03 mole. So what is the purity of the sample? So look at this, we have KClO3. These on heating gives you KCl plus oxygen gas. Question says initial mass of sample taken is 4.9 gram of KClO3 is given, and question clearly said this is impure. That means some amount of impurity is also present in this. When this decomposes to give you KCl and oxygen, so mass of KCl form is 4.9 gram and number of moles of oxygen is 0.03 mole. So we have to convert this into mass. So this is equals to 0.03 into 32 gram. So this comes out to be 0.96 gram. So look at this. This is impure sample, but KCl and oxygen is coming from pure KClO3. Now, since the mass of the product form given is, that means there must be conservation of the mass. Therefore, from the conservation of mass, the mass of pure KClO3 should be equals to mass of KCl plus mass of oxygen form. The mass of KCl is 4 point, also this is 1.49 plus mass of oxygen is 0.96 gram. So this comes out to be so look at this. So mass of pure sample is 2.5 gram. Mass of impure sample is 4.9. So therefore, percentage purity of the sample, mass of pure sample divided by mass of impure sample into 100. So this is the percentage purity of the sample. So this is how we apply conservation of mass to define the percentage purity of any given sample. Now, in a similar reaction, question says a sample of magnesium carbonate is 50% pure. So purity of the sample is 50%. If on heating 4 gram of magnesium oxide and 4.4 gram of carbon dioxide are formed, what was the amount of magnesium carbonate taken? So question says sample of magnesium carbonate is only 50% pure. Now take a sample of magnesium carbonate on heating. This gives you magnesium oxide and carbon dioxide. Magnesium oxide gives you 4 gram and carbon dioxide is 4.4 gram. Then what was the amount of or the mass of magnesium carbonate taken? Now we have looked at this. Magnesium carbonate on heating gives you magnesium oxide plus carbon dioxide. Let the mass of this impure sample be x gram, we have to define. But this gives you how many mass of magnesium oxide? 4 gram. And carbon dioxide 4.4 gram. But this magnesium oxide and carbon dioxide is exclusively coming from pure magnesium oxide, magnesium carbonate. So therefore, from conservation of mass, mass of pure magnesium carbonate will be equal to mass of magnesium oxide plus mass of carbon dioxide. So this is 4 plus 4.4 gram, so that is 8.4 gram. So this is the mass of pure magnesium carbonate. This is from this. Now we have to find the same mass of this sample. So therefore look at this. This is question said this is only 50% pure. That means therefore from the given condition 50% of this X will be equals to 8.4 gram. So therefore X is equals to 2 times 8.4 gram, that is 16.8 gram. So if you take this 16.8 gram, this on heating gives you 4 gram of magnesium oxide and 4.4 gram of carbon dioxide, whose purity of the sample is 50%. So this is how we apply law of conservation of mass in chemical reactions. So once we learn this conservation of mass, now let's go to second law. The second law is law of constant composition. By mass. Law of constant composition by mass. This law of constant composition by mass, this is also known as law of definite proportion by mass. So in many of the books simply says law of constant composition or law of definite proportion, but actually this is law of constant composition by mass or law of definite composition or proportion by mass. This law was given by Joseph Proust. So this was the scientist who gave this law of constant composition by mass. Now look at this. This law of constant composition by mass or law of definite proportion by mass or law of definite composition by mass or law of definite percentage composition by mass, this law is applicable only for pure substance. Pure substance. This law cannot be applied in impure substance. This is applicable only for pure substance. So suppose, let me give you some example first. Suppose take a pure sample of carbon dioxide. We have a pure sample of carbon dioxide. Now in this pure sample of carbon dioxide we have carbon and oxygen. So we have 1 atom of carbon and 2 atom of oxygen. So mass of 1 atom of carbon is 12 U. Mass of 2 atoms of oxygen is 32 U. So look at this. We have a pure sample of carbon dioxide. This pure sample of carbon dioxide contains 1 atoms of carbon, that is 12 U. 2 atoms of oxygen, that is 16 into 2 U. Now look at this. Take the mass ratio, mass of carbon to that of mass of oxygen in this pure sample, that is carbon dioxide. So this ratio is 12 by 32. So look at this, 12 by 32. So look at this, mass of carbon is 12, mass of oxygen is 32. So ratio of mass of carbon to that of mass of oxygen is 12 by 32. So the common factor is 4. So cancel it by 4. 4 3 is 12, 4 is 32. So look at this, whenever the combining mass ratio of carbon oxygen is 3:8, that is carbon dioxide. If the mass ratio of carbon and oxygen is something other than 3:8, that cannot be carbon dioxide. So whenever we talk about this pure substance carbon dioxide, the combining atomic mass ratio of carbon and oxygen in this pure sample is always 3:1. Now this 3:1, it is simple whole number, that is whole number ratio. Take another example. Take this carbon monoxide. We have carbon and we have oxygen. So we have one atom of carbon, so mass is 12U. We have one atom of monoxide, that is 16U. So we have a pure sample of carbon monoxide, in which we have one atom of carbon with mass 12U. We have one atom of oxygen with mass 16U. Now take the mass ratio. Mass of carbon to that of mass of oxygen, that is 12 is to 16. That is 3:4. So if the combining atomic mass ratio of carbon oxygen in any given sample is 3:4, so this cannot be carbon dioxide, this has to be carbon monoxide. So irrespective of the source of this carbon monoxide, a pure sample of carbon monoxide will always have this mass ratio, that is 3:4. So if we have this 3:4, then look at this constant composition. Composition is always constant for a pure sample, and we have a constant composition means we have this mass ratio fixed. If the mass ratio is fixed, then the proportion, that is 3:4, or we can say the percentage of carbon. So percentage of carbon is 3/7 into 100, and the percentage of oxygen is 4/7 into 100. So this percentage will always be fixed. That is for a pure sample. Take one more example. Take this a pure sample of water molecule H2O. We have looked at this hydrogen and we have this oxygen. One molecule of H2O contains two atoms of hydrogen and one atom of oxygen, and mass of two atoms of hydrogen is 2U, mass of one atom of oxygen is 16U. So the mass ratio of hydrogen to that of oxygen in a pure sample of water is 2/16, that is 1:8. So if this ratio is not maintained, that means the compound or the molecule cannot be a pure sample, or molecule cannot be a water. Whenever we have a pure sample of water, this ratio has to be maintained 1:8. That is, percentage of hydrogen is 1/9 into and percentage of oxygen is 8/9 into. So these percentage should be fixed. So this is what we call as law of constant composition by mass, or law of definite proportion by mass, or law of definite composition by mass, or law of fixed percentage composition. And this law is given by Jessup-Ross, and this is applicable only for pure substance. So now coming to the statement of this law of constant composition. So for a pure sample, irrespective of the source of origin, every pure sample, irrespective of its source of origin, will always have simple whole number ratio of the masses of the combining atoms. I repeat, for a pure substance, irrespective of the source, the combining atomic mass ratio will always follow a simple whole number. So this is what we call as law of constant composition, or law of definite proportion by mass. So once we know this law of definite proportion or constant composition by mass, let me explain this by use of another example. So let me explain by use of this question. 1.4 gram of iron reacts with 0.8 gram of sulfur directly to form iron sulfide FeS. So 1.4 gram of iron combines with 0.8 gram of sulfur directly to form FeS iron sulfide. A 5.6 gram of iron was dissolved in dilute HCl and excess of potassium sulfide was added. So we have 5.6 gram of iron and this was dissolved in dilute HCl, and to the solution excess of potassium sulfide was added. How much iron sulfide was formed in the second case? How much iron sulfide was formed in the second case if law of definite proportion is followed? Is followed. So we have this question clearly says law of definite proportion by mass is to be followed by this reaction. We have two cases here. In the first case, 1.4 gram of iron reacts with 0.8 gram of sulfur to give you iron sulfide. In another sample, another set of experiment, 5.6 gram of iron was dissolved in HCl and excess of potassium sulfide was added. Now question says how much of iron sulfide was formed in the second case. Now question also says law of definite proportion is also followed by this reaction. That means the proportion of the mole ratio of iron and sulfur in both the case should be exactly same. But if law of definite proportion is followed, the mole ratio of iron and sulfur in the first case should be exactly equal to the mole ratio of iron and sulfur in the second case. So we can tackle this problem in this way. Number of moles of iron in the first case divided by number of moles of sulfur in the first case should be exactly identical to number of moles of iron in the second case divided by number of moles of sulfur in the second case. So mole ratio should be completely followed. So number of moles of iron, that is mass divided by molar mass. Number of moles of sulfur, 0.8 divided by 32. Mole of iron, that is 5.6 divided by 56. Let the mass of sulfur be x divided by 32. So from this difference we can find the value of x. So x by 32 is equals to 5.6 by 56 into 0.8 by 32 divided by 1.4 by 56. So 56 will cancel out. So therefore, x equals to 5.6 into 0.8 into 32 divided by 1.4 into 32. Again 32 will cancel out. This is 4. So we have 3.2. So the mass of sulfur in the second case is 3.2 gram. So therefore, mass of FeS formed will be equal to mass of iron plus mass of sulfur. So mass of iron is 5.6, mass of sulfur is 3.2. So we have 8.8 gram. So look at this. Here we are converting this gram into moles because since law of constant composition is followed in both the case iron sulfide is formed, so the mole ratio of iron sulfur in both the cases should be identical or same. So from this we define the mass of sulfur, and once we define the mass of sulfur, we define the total mass of iron sulfide formed in the second case. So this is how we apply law of constant composition by mass. One more question. So this question says C is a compound 30 gram of this compound C on analysis gives 10 gram of A and 20 gram of B. That means C is formed by a combination of A and B. If 15 gram of A reacts with 50 gram of B, what mass of C will be formed? So we have a reaction in which A combines with B to give you C. So the first case says 30 gram of C on analysis gives you A 10 gram, B 20 gram. If this is the case, then if 15 gram of A reacts with 50 gram of B, then what is the mass of C formed? So we have this case 1. So case 1 says mass ratio of A and B. So this is 10 by 20. So we have 1:2. Now the same mass ratio must also be followed in second case. So whenever, that means 1 gram of A will always combine with 2 gram of B. That is 1 gram of A combines with 2 gram of B. So in the second case, you have 15 gram of A reacting with 50 gram of B. So 15 gram will require how many grams of B? If 1 gram A combines with 2 gram, then 15 gram of A requires 30 gram of B. So 15 gram A will combine with 30 gram of B. If 15 gram A combines with 30 gram, then the mass of C formed will be 15 plus 30, that is 45 gram. That means out of this 50 gram of B, only 30 gram will be consumed and the remaining 20 gram will remain unreacted. So again, look at this, we are using C is coming from two different sources, but E and B always ratio should be 1:2. So this is how we use law of definite proportion by mass. Now after this law of definite proportion by mass, we have next law, and the next law is law of multiple proportion by mass. Multiple proportion by mass. First one says definite proportion by mass. This is multiple proportion by mass. This multiple proportion by mass, this was given by John Dalton. And this law, in the constant composition by mass, we take a pure compound. And in the pure compound, in the pure symbol, we take the mass ratio of the combining atoms. That comes out to be simple volume ratio. Whereas in this law, multiple proportion, we have combining element is same combining element is giving you more than one product. In the first case, we have only one compound pure sample, and in the pure sample, we get the mass ratio of combining atoms. Whereas in this law, multiple proportion by mass, the combining elements are same combining element. This is giving you more than one product. So we'll take the mass of the mass ratio of the combining atoms, keeping the mass of one of the components fixed. So let me just explain by taking example first. We have looked at this carbon combines with oxygen gas, and this gives you carbon monoxide and carbon dioxide. So we have combining element is same carbon option, but this is giving you more than one product. So this law is applicable only when same combining atom is giving you more than one product. So if you look at this, we have carbon, we have oxygen. We have one atom of carbon, mass is 12U. We have one atom of oxygen, mass is 16U. In the carbon dioxide, we have one atom of carbon, that is 12U. Two atoms of oxygen, that is 32U. Now, in these two combining atoms, carbon and oxygen, keep the mass of one component fixed. So for a fixed mass of one component, we take the mass ratio of other. If this comes out to be simple whole number ratio, then this is what we call as law of multiple proportion by mass. Now, look at this. Keeping the mass of carbon at 12U, we take the mass ratio of oxygen. Mass of oxygen is carbon monoxide by mass of oxygen carbon dioxide. So mass of oxygen, because 12 unit requires 60. In the second, 12 unit requires 32. So this comes out to be simple whole number ratio. So according to this law, for same combining elements giving you more than one product, the mass ratio of one of the components for a fixed mass of other component will always be a simple whole number ratio. So keeping the mass of carbon at 12, you can keep the mass of carbon at 12, any value, whatever you choose. We can also carry that for this oxygen only. Keep the mass of oxygen fixed, we can take the mass of oxygen carbon. So 16 requires 12, 32 requires 12, so 16 will require 6 unit, 32 requires 12, so 16 will require half of this value. Now keep the mass of oxygen fixed at 16, take the mass ratio of carbon. So mass of carbon and carbon monoxide, mass of carbon and carbon dioxide. So this is 12 by 6. Again, this comes out to be 2:1 ratio. So whenever two elements combines to give you two or more than two compounds, the combining atomic mass ratio of one component for the fixed mass of other component will always bear a simple whole number ratio. That is what we call as multiple proportion by mass. Let me explain by use of another example here. Is hydrogen combines with oxygen, and this gives you H2O and H2O2, hydrogen peroxide. Look at this. We have hydrogen, we have oxygen. Two atoms of hydrogen means 2 mass unit. One atom of oxygen, 16 mass unit. Two atoms of hydrogen, 2 mass unit. Two atoms of oxygen, 32 mass unit. Now keeping the mass of hydrogen fixed. Keep the mass of hydrogen fixed at 2 units. For the fixed mass of hydrogen, the mass of oxygen in H2O divided by mass of oxygen in hydrogen peroxide, this ratio 16 is to 32, that is 1 is to 2. This is again simple whole number ratio. Take this example, sulfur plus oxygen gives you sulfur dioxide, sulfur trioxide. We have sulfur, we have oxygen. One atom of sulfur, 32 mass unit. Two atom of oxygen, 32 mass unit. One atom of sulfur, 32 unit. Three atoms of oxygen, 48 unit. So keep the mass of sulfur fixed at 32. So take the mass ratio of oxygen. So this is 32 by 48. It equals to 3. So for a fixed mass of sulfur, the mass ratio of oxygen in this sulfur dioxide and sulfur trioxide always bears a simple whole number ratio. So again, I'm emphasizing here. Here we are taking combining elements to be same. For the same combining element is giving you more than one product. So in the product, we keep the mass of one of the component fixed. For the fixed mass of one combining atom, we take the mass ratio of other combining atoms. So that mass ratio will always be a simple whole number ratio. If that ratio is simple whole number ratio, then this is what we call as law of multiple proportion by mass. So this is law of multiple proportion by mass. Now let's see how we can use this law of multiple proportion by in numerical problems. Question. The question says a metal M forms two oxides A and B, and the data for these two oxides is given. Oxide A mass is 1.45, oxygen combined is 0.56 liter at S2P. Oxide B mass of oxide is 1.125, oxygen combined is 0.56 liter at STP. If law of multiple proportion was followed, identify the oxides. So this is mass of oxide given in gram. Oxygen combined is given in terms of liter at STP. So we have to convert this into mass. So look at this is 0.56 liter. So at STP, number of moles is 0.56 divided by 22.4 liter. Volume occupied by the gas at STP divided by molar volume, and this number of moles is equal to mass by molar mass. So therefore mass of oxygen is equal to 0.56 by 22.4 liter into 32. So this comes out to be 56 into 32 into 10 to the power minus 1 divided by 22 4. So this is 448, that is 0.8 gram. So 0.56 liter of oxygen is corresponding to 0.8 gram. Now, so in the first oxide A, mass of oxide is 1.45, mass of oxygen is 0.8, therefore mass of metal M will be equal to 1.45 minus 0.8. This is total mass of metal and oxygen, this is the mass of oxygen. So this comes out to be 0.65. So therefore look at this, metal oxygen ratio in the same compound oxide B, mass of metal is 1.125 minus 0.8, 0.325. So we have mass of metal, mass of oxygen. We have mass of metal, mass of oxygen. So in this case, ratio. Now let's take the ratio. So mass of, for a fixed mass of oxygen is fixed, we take the mass ratio of metal. Metal in A divided by mass of metal in B. Now divide this mass by molar mass, we take number of moles of M in A divided by number of moles of M in B. So this equals to 0.65 divided by 0.325. So this comes out to be approximately 2:1. So mass of oxygen is fixed. So for a fixed mass of oxygen, we get the mass ratio of these two metals A and M in A and B. Now, since we have to define the formula, so we convert this mass into molar mass. So number of moles, we divide this each by molecular mass. So mass divided by molecular mass, this comes out to be number of moles. So mole ratio of metal in A and B is 2:1. So therefore, formula of A is M2O and that of B is M4. So this is how we derive the formula of the compound. So let's take one more example here. So we have a sample of methane. A sample of methane contains 11.4 gram of carbon and 3.8 gram of hydrogen. Another sample of hydrocarbon, that is ethane. This ethane contains 4.47 gram of carbon and 1.118 gram of hydrogen. So that these two substances obey law of multiple proportion. Proof law of multiple proportion. So we have a sample of methane and sample of ethane. In the sample of methane, we have 11.4 gram of carbon and 3.8 gram of hydrogen. In the sample of ethane, we have 4.48 gram of carbon and 1.11 gram of hydrogen. Now, take this methane and ethane. So we have carbon-hydrogen ratio. That means, let's find, keeping the mass of hydrogen, we'll find the mass of carbon. So 3.8 gram of hydrogen requires 11.4 gram of carbon. So for this CH4, mass ratio of carbon and hydrogen. So this comes out to be 11.4 divided by 3.8. So this comes out to be 3. In the second sample, that is C2H6. So this is mass of carbon required for fixed mass of hydrogen. That is, for 1 gram of carbon we require this. So 1 gram of hydrogen require this grams of hydrogen. In this C2H6, take the mass ratio of carbon and hydrogen. That means 4.47 gram carbon and we have 1.18 gram hydrogen. So 1.118 gram hydrogen requires 4.47 grams. So for 1 gram, what is the requirement for carbon? So therefore, look at this mass of carbon to that of mass of hydrogen. We have this 4.47 divided by 1.118. So we have this 4.47 divided by 1.118. So again, this is approximately coming to 4. Now, so for a fixed mass of hydrogen, means for 1 gram of hydrogen, mass of carbon requires 3. For 1 gram of hydrogen, mass of carbon requires 4. So therefore, mass ratio of carbon in CH4 divided by mass ratio of carbon in C2S6. This comes out to be 3:4. This is a simple whole number ratio, and this proves it is given data. What is given data in these two compounds? Law of multiple proportion is obeyed. So look at this. Question is slightly modified. Don't get confused. I'm taking this mass of carbon to that of mass of hydrogen. So we are having 3.8 gram hydrogen requires 11.4. So 1 gram will require 11.4 divided by 3, and that is for 1 gram of hydrogen, what is the mass of carbon required? Same. For 1 gram of hydrogen, what is the mass of carbon required? So we, in the both case, we are keeping the mass of hydrogen fixed. For the fixed mass of hydrogen, what is the mass of carbon in these two compounds? And this comes out to be simple whole number ratio. So since the whole number ratio is obeyed, so this follows law of multiple proportion by mass. So this is law of multiple proportion by mass. Once we have this law of multiple proportion by mass, we have next law, that is Gay-Lussac's law of combining volume. Gay-Lussac's law. or simply say Gay-Lussac's law of combining volumes. So first of all, this Gay-Lussac's law of combining volume, this is name of the scientist who designed this law, and this is applicable only for gas. This law is not applicable to solids and liquids, whereas first law, second law, third law, that is applicable to solid, liquid as well as gas, whereas law of combining volume is applicable only for gases. So, we have a reaction in which gases, species are involved. In that case, we can apply this law of combining volumes. So take this. We have carbon solid combines with oxygen gas, and this gives you carbon dioxide gas. So look at this, reaction is balanced. In the balanced chemical equation, if the gases are measured at the same temperature and pressure, so condition is the gases involved in the chemical reaction should be at same temperature pressure condition. So look at it, this is solid, so the law cannot be applied here. So we have a gas, we have a gas. In this balanced chemical equation, the coefficient of oxygen is 1. So coefficient can also be considered to be the volume. So we have look at this. One volume of oxygen will always combine with carbon to give you one volume of carbon dioxide. So therefore look at this. Volume of oxygen to that of volume of carbon dioxide. This is always 1:1 ratio. This is simple whole number ratio. Take this example. We have carbon monoxide gas combines with oxygen gas, and this gives you carbon dioxide gas. The reaction is not balanced. First, we have to balance the reaction. So we have this. So the reaction is balanced. We have 2 atoms of carbon on each side, 4 atoms of oxygen on each side. All the components are gas. All these 3 gases are measured at same temperature pressure condition. Then look at this. We have in the balance reaction 2 volume of carbon monoxide always combines with 1 volume unit of oxygen, and this always gives you 2 volume units of carbon dioxide. So therefore look at this. Volume of carbon monoxide is to volume of oxygen is always 2:1. Now this can also be extended to products also. Volume of carbon monoxide is to volume of carbon dioxide. This comes out to be 1:1. Volume of oxygen to that of volume of carbon dioxide. This comes out to be 1:2. So if you look at this, the volume ratio of the combining reagents or products always bears a simple whole number ratio. So this law says whenever gases react, specifically this is only meant for gases. So says whenever gases react, they always react in simple whole number ratio by volume. I repeat this statement. According to Gay-Lussac's law of combining volume, whenever gases react, they always react in simple whole number ratio by volume. So these gases, whenever they combine in a chemical reaction, the volume ratio of gases component will always bear a simple whole number ratio. So let's see how we apply this in solving problems. Suppose we have this reaction, carbon monoxide gas react with oxygen gas, and this gives you carbon dioxide gas. Initially in a reaction container, 400 ml of carbon monoxide. Suppose this 400 ml of carbon monoxide is mixed with 300 ml of oxygen gas in a reaction container. Reaction takes place and this gives you product, that is carbon dioxide, according to this balanced reaction. Question says, during the course of reaction, only 80% of carbon monoxide is converted to product. So initial container contains 400 ml of carbon monoxide and 300 ml of oxygen. Both are mixed in a container, reaction takes place and the product forms according to this balanced reaction. But the condition is only 80% of the carbon monoxide is converted into the product. So what is the composition of the mixture? What is the composition of the mixture? Means after this reaction, what is the volume of carbon monoxide? Reacted, what is the volume of oxygen? What is the volume of carbon dioxide formed? So look at this. The components are gases, so we can easily apply this Gay-Lussac law of combining volume. So according to look at this balance reaction, 2 volume of carbon monoxide always reacts with 1 volume of oxygen, and this gives you 2 volumes of carbon dioxide. But the question says, from this initial 400 ml of carbon monoxide, only 80% is converted. So therefore look at it. Volume of carbon monoxide reacted is equal to 80% of the initial volume, that is 320 ml is reacted. So volume of carbon monoxide reacted is 320. So volume of carbon monoxide left is 400 minus 320, so 80 ml is left. Now look at it. 2 volume of carbon monoxide always gives you 2 volume of dioxide. So 1 volume will give you 1 volume. So therefore, volume of carbon dioxide formed is equal to volume of carbon monoxide reacted is equal to 320 ml. Now look at this. Along with this, some oxygen has to be consumed. So look at this. Every 2 volume of monoxide requires 1 volume. So 1 volume of monoxide requires half volume of oxygen. So therefore, volume of oxygen reacted is equal to half of volume of monoxide reacted, because this 2:1 ratio. So this is 320 by 2, that is 160 ml. So 160 is consumed. So how much is left? So we have 300 minus 160, that is 140 ml. So composition of mixture is 140 ml oxygen is left, 320 carbon dioxide is formed, and 80 ml carbon monoxide is left after this reaction. So this is how we apply law of combining volume for reaction involving gases. After this, so first thing is to apply this law of combining volume, the reaction should be completely balanced. So solving of these type of questions, the reaction should be completely balanced first. So without balancing the reaction, we can apply this law of combining volume. So in the balanced chemical reaction, the coefficient of the gas will be assumed to be the volume ratio. One more example. In a given chemical reaction of this, nitrogen gas reacts with oxygen to give you N2O gas. This is the balanced chemical equation. Question says, in this reaction, if 45.4 liter of N2 is mixed with 22.7 liter of oxygen, then what is the volume of N2O formed? So if you look at this, N2O combines with oxygen to give you N2O gas. Balance is balanced. We have coefficient 1, we have coefficient 1. So if you look at this, 1 volume of N2 will react with half volume of O2. This will give you 1 volume of N2O. So if you look at this ratio is 1:1. So volume of N2 used is 45.4. Oxygen is 22.7. Look at this. 1 volume requires half, so 45.4 will require half of this value, that is 22.7. So volume of N2 react is 45.4, so the volume of N2O form will also be same, that is 45.4 liter will be formed. So simply look at this, by use of this balanced chemical equation we can find what is the volume of the product form, or if the product volume is given, what is the volume of reactant reacted. So this is law of combining volume, which is also known as Galison's law of combining volume. Next law is Avogadro's law. Again, this Avogadro's law is applicable only for gas. This is not applicable to solids as well as liquids. So the last two law, Galison's law and Avogadro's law, that is applicable only for gaseous reacting species or gaseous, whereas remaining laws are applicable to solids, liquids as well as gas. So according to this Avogadro's law, at a given temperature and pressure, so temperature, pressure remaining constant, temperature and pressure remaining constant, then if temperature and pressure of a given gas is constant, then the volume occupied by the gas is directly proportional to number of moles of gas. So volume is directly proportional to number of moles of gas provided temperature and pressure of the gas remaining at constant, or we can say volume occupied by the gas is directly proportional to number of molecules of gas. So pressure, temperature remaining constant, volume is directly proportional to number of moles or number of molecules of gas. But if suppose volume is also constant, so if pressure, temperature constant, volume is proportional to number of moles. But if volume is also constant, then number of moles or number of molecules is also constant. That means if we take different samples of gas, all these gas are kept at identical conditions of temperature, pressure and volume. We take different gases. All these gases are kept in different containers, and all the containers are maintained at same volume, same temperature, same pressure. Then according to Avogadro's law, the number of molecules or the number of moles of gas in different containers containing different gases will always be same. So another modified form of this Avogadro's law is equal volumes of all gases under identical conditions of temperature and pressure contains equal number of moles of gas or equal number of molecules of gas. That means, suppose look at this, we have a container A, container B and container C. Container A contains suppose hydrogen gas, B contains helium gas. Suppose this contains hydrogen, oxygen and helium. So all containers are in same volume, temperature T, pressure P. This constant is fixed. So we have three containers containing three different gases: hydrogen, helium, and mixture of gases. All containers are having same volume. They are placed at same temperature and pressure. Then the number of molecules of hydrogen will be equals to number of molecules of helium will be equals to number of molecules of this mixture, or you can say number of moles of gas will be same. So therefore look at this, for this case number of moles of molecules of hydrogen is to number of molecules of helium is to number of molecules of this mixture, logically 1:1:2. So this law first says pressure, temperature remaining constant, volume is proportional to number of moles or number of molecules of gas. But if you have different containers containing different gas or a mixture of gas, but if they are kept in same temperature, pressure, and volume condition, then the number of molecules or the number of moles of gas will be same, though we have different gases. Now, some important points from this Avogadro's law is we develop a quantity known as vapor density. Vapor density is simply written as VD. So this vapor density is not a density but a pure number. This is the ratio of two density. Density of a given gas divided by density of hydrogen gas at the same temperature and pressure. So this ratio, numerator is density, denominator is density, so we have a ratio of density, so ratio of two densities, so this cannot be a density. This is a pure number without any unit. So vapor density is density of a given gas divided by density of hydrogen gas, both measuring at the same temperature and pressure condition. Now, for gases, we develop a relation between molecular mass and vapor density. So molar mass of gas is always equal to 2 times its vapor density. It's a very important formula that we often use in chemical calculation. For gas, if vapor density is given, then we can easily define what is the molecular mass of the gas. So molecular mass of the gas is equal to 2 times its vapor density. Second, we have molar mass. So 1 mole of ideal gas at STP, standard temperature pressure or normal temperature pressure. The volume occupied by 1 mole of ideal gas at STP, that or normal temperature pressure, is always a fixed quantity. This is equal to 22.4 liter. STP temperature is 273 Kelvin, pressure is 1 atm. So we have different gas. So 1 mole of an ideal gas always occupies a volume of 22.4 liter at STP. So look at this. 1 mole is equivalent to 22.4 liter for gas. Now, mass of 1 mole is known as molar mass. So this is equal to gram molar mass. So 1 mass of 1 mole or mass of 1 gram molecule or 1 gram atom, that is gram atomic mass or gram molecular mass, will always occupy the volume of 22.4 liters. So this can be used for mass volume conversion. So this is 1 mole of an ideal gas at STP always occupies a volume of 22.4 liter. So mass of 22.4 liter of an gas That density is equals to gram molecular mass or simply molecular mass or gram atomic mass or atomic mass. So this is vapor density and molecular mass. So these we are going to often use in chemical calculations. Let's see use of this. Question says we have unknown gas X and unknown gas. The vapor density of an gas is 5 times the vapor density of oxygen gas. So question says we have an unknown gas whose vapor density is 5 times the vapor density of oxygen. Then question says if the unknown gas is triatomic, what is the atomic mass So question says we have an unknown gas. This unknown gas is triatomic, means one molecule of this unknown gas contains 3 atoms. Question further says the vapor density of gas is 5 times the vapor density of oxygen. Then what is the atomic mass of unknown? So let this unknown gas be X. So question says this is triatomic. So one molecule of this unknown gas contains 3 atoms. So question says vapor density of this X3 is equals to 5 times the vapor density of oxygen. So we have looked at this vapor density and molecular mass. So if we have vapor density of oxygen, then vapor density of oxygen is half of molecular mass. Molecular mass of oxygen divided by 2. So we have 5 into 32 divided by 2. So this is the vapor density of X3. So therefore look at this. Molecular mass of this X3 is equal to 2 times its vapor density. So therefore this is equal to 2 into 5 into 32 divided by 2. So this is 160 gram. So the molecular mass of this unknown compound X3 is 160. But one molecule contains how many atoms? 3. So therefore atomic mass of X is equals to molecular mass divided by 3. So this is how we define molecular mass, and from this molecular mass we define atomic mass provided this atomicity, how many atoms are present in a molecule is given. So these are the laws of chemical combination. And what is the implication of these laws of chemical combination statement and the examples problems related to laws of chemical combination. So these laws of chemical combination basically governs the chemical reactions. Okay, thank you all.